started to talk about the water wheel of Willem Malkus last time. And we saw that it can behave chaotically, at least in a complicated way in our video. But so today I would like to show some quick analysis of the water wheel equations that we derived last time, and then pretty quickly abandon them for the equations that everyone studies instead of them, which are the Lorentz equations that are very closely related. And so we'll start developing some of the elementary properties of the Lorentz system today. And then that will occupy us for the next few lectures. So as far as the water wheel, you may remember we ended, I wouldn't say on a cliffhanger, because we actually got to a miracle, right? We saw that three equations out of an infinite set of ordinary differential equations, three of them decoupled exactly from the rest. And here's what they were. So we had A1 dot is omega B1 minus K A1, and B1 dot was negative omega A1 plus Q1 minus KB1, and omega dot is negative nu omega over I plus pi gr A sub 1 over I. So lots of symbols there. Hopefully you remember the main ideas, which were that the omega referred to the angular velocity of the water wheel, how fast it was turning, either left or right. And A1 and B1 are the amplitudes of the first harmonics of the water distribution around the rim of the wheel. I think the way we set it up, A1 would have been the coefficient of sine theta. And yeah, that's right. And B1 was the coefficient of cosine theta. And then all the rest of the things in there are parameters. Okay, so I was the moment of inertia. I think nu was the, well, let's see, maybe the leakage rate? Or, is that right? No, I guess nu is the brake, the strength of the rotational damping, and K was the leakage rate. R is the radius of the wheel. G was the effective strength of gravity in the plane of the wheel. And I was the moment of inertia. Okay, so anyway, there we are. Now, we just have these three equations, but then remember there were infinitely many others. In homework, I have an exercise where you can look at those others. So you'll look, or maybe you already have looked, I don't know how far you've gotten, but you can look at the behavior of these other modes. AN and BN for n greater than 1. And so, but we're not going to say anything more about them here. They don't feed back into these three equations, so we don't really need to pay attention to them right now. Okay, now let's look at these three equations. It's our first three-dimensional dynamical system, and I guess your knee-jerk reaction would be, let's look at some fixed points, and then maybe even we would want to linearize around them. Actually, I think I won't do that. We'll save that for the Lorentz system. But just to see what fixed points can occur, takes a little bit of algebra. And then we'll have to think about what these fixed points mean for this 3D system. All right, so algebraically, if we have A1 dot equals 0, then that implies A1 is omega B1 over K. And here I'm going to just number my equations because there's lots of little easy substitutions we're going to need to make. So let's call this equation 1. Then B1 dot equals 0 says omega A1 is Q1 minus KB1. I think I forgot to say Q1 would be the first harmonic of the inflow from the manifold that was shooting the water into the water wheel. First harmonic in cosine theta, that amplitude. Okay, anyway, so we have that. Then the third equation will be omega dot equals 0. And that says A1 is nu omega over pi gr. And now we want to start cleaning those up. You can notice various things can be done to eliminate some of the, that is, we'd like to solve for A1, B1, and omega. And one thing you could do is you could combine 1 and 2 to get rid of A. So eliminate A1 from 1 and 2. That is to say, you could take this expression for A1, substitute it in here in the equation 2, and then solve for B1, and you get that B1 is KQ1 over omega squared plus K squared. So I'll call that number 4. And then really, I should be putting stars on these, right? This will be A1 star, B1 star, omega star. But let me skip the stars. We know that these are fixed points. So I got B1. Then another thing you could do is, notice we have here 2 equations for A1 in 1 and 3. And so 1 and 3 together imply that since they're both expressions for A1, that omega B1 over K equals nu omega over pi gr. And that's an interesting equation because you can see that it has one solution that's trivial in the sense that it works for all values of parameters. That is, omega equals 0 is a solution of this. Right, since there's an omega in the numerator on both sides. So we either have omega equals 0, or if it's not 0, let's divide it out. Then we would have, well, we could solve for B1. And we'll get B1 is K nu over pi gr. And I'll call that second equation 5. And so we have to think about 2 cases here. Is there any question about anything in the algebra so far? Not a whole lot going on, just solving it. OK, so let's stare at these 2 cases now. What does the omega equals 0 case mean? Well, so if omega is 0, let's just read off what the other values are. Looking at the equation for A1, here number 3, you see that that says A1 is 0. And what about B1? Then B1 from this equation 2 would just be Q1 over K. So let's think about what that's saying. Omega equals 0 means the wheel is not turning. It's just sitting there. And to have a fixed point, it says that there will be no sinusoidal component of the water distribution. That is, it's just evenly distributed, or that is to say, it's symmetric around the top with a first harmonic given by B1 is Q1 over K. So all that's going on in this case is that the water is pouring in and draining out in a steady way, right, with inflow Q1 balanced by outflow rate K. And so this is a fixed point in the sense that nothing about the water distribution is changing. It's just coming in, going out. The histogram of the green bars around the chambers, that'll just be, unchanging. And then the wheel is motionless. So this is a case of no rotation and leakage balances inflow. And what's interesting is that this solution always exists, no matter what the values are of the other parameters. Now, we're not saying it's stable, just saying that it exists. But you have to be aware that this trivial kind of motionless solution is always there as a possible fixed point. Yes? Yes. In the video, I spun the water wheel initially, and you might have wondered, why did I do that? And the honest reason is that if I leave the water wheel just sitting there and turn on the switch so that the water starts pouring in principle what should happen is that the water should go in and the wheel, since this will turn out under the conditions I had the thing set initially to be an unstable equilibrium, the wheel should have started filling up with water and then the top will get heavy and it's a little bit biased to one side or the other by chance and then it will start rotating that way. Now, in reality, what often happens, and what I wanted to avoid, was that because there's some stickiness in the wheel that's not modeled by anything we wrote down, it'll start filling up, and then it won't turn, and it'll just start spilling water all over the place. And it just, I thought, would make bad cinema. So I gave it a little spin, because I knew that that was the steady state it wanted to achieve. That is actually, as a matter of fact, for those equations, a global. The only steady states for that system are either steady rotation, rotating one way, or the other way. And I kind of want to nudge it in that direction. Yes? It's not just because of the brake. I mean, the brake is, if the brake behaved in the ideal way that we had described in the equations, this would not happen. But I think there's some non-ideal aspects of the brake, like, you know, maybe along the lines of coefficient of static friction is different from dynamic friction or something like that. So so I fudged it a little by starting it rotating. You caught me. Yeah. Any other comment? Yes. So there's that. Now the other case then is suppose omega is not 0. So that is, let's just reiterate here that we're not saying if this is stable. We'll analyze that later. So not any comment at the moment about the stability of this fixed point. Now, if omega is not 0, then we're in the other case, which is this one, where B1 is this value. So we have equation 5. And so then B1 is K nu over pi GR. But on the other hand, we have this equation 4 for B1. So that's another equation for B1. That says that it's supposed to be KQ1 over omega squared plus K squared. And then you can see you can cancel out the K's. And the interesting thing is to look for the value of the variable omega, which if you solve for omega, then you get omega squared equals pi GR Q1 over nu minus K squared. So let's put that in a box. That is, it's predicting what the rotation speed will be in steady state in terms of these other parameters. And you'll notice that, in fact, it's not an expression for omega, but omega squared, which is to say if omega is a solution, so is negative omega, which means it can rotate just as well in one direction as the other. Plus or minus or omega are both solutions. Now, except that this expression on the right might be negative, right? So that's a case where you wouldn't have this solution. And so these two solutions, plus or minus omega, corresponding to steady rotation, in either direction. They exist if and only if the right-hand side is positive. And so saying that the right-hand side is positive, a nice way to put that would be to say that pi g r q1 over k squared nu is greater than 1. That's a very interesting way to say it, because now we're comparing this big freight train of parameters to the number 1. That is, this is a dimensionless group. Not obvious a priori that that would have no units, but it, as you can see, it doesn't. It's just being compared to the number 1. So this dimensionless group is a famous thing. Not famous in the context of the water wheel, since nobody studies the water wheel, except for Malkus and people at MIT, and now us. But still, I've used the notation that people use in another subject, which is fluid dynamics, where people study convection. And so this is the Rayleigh number in that context. Or that is to say, this would be the analog of the Rayleigh number in this water wheel analog of convection. Yes? You had a question?
Yeah.
Q, remember that the water was flowing in from the overhead nozzles from the manifold. So we had written Q of theta, that is, it was a function of, the water wasn't coming in everywhere over the wheel, only at certain places where the manifold was. And so we wrote Q of theta was the sum of Qn cosine theta, or sorry, cosine n theta, 0 to infinity. So it's the first harmonic of the water inflow distribution. It's Q1 is the coefficient of cosine of theta. Okay. But think of it as inflow. It's the thing that's driving the wheel. Is there another question? Okay. So anyway, we've got this interesting dimensionless group, and as I say, in fluid dynamics, where people study convection, it's the Rayleigh number. Now, okay, so if you don't know about convection, let me just say briefly what that is. You know the basic fact that hot air rises, right? The sun is beating down on the earth, let's say. The ground gets hot. The air near the ground gets warmer than the air way up high. Hot air rises. Now, it doesn't necessarily have to rise. That is, there could be a state where the air is just very warm near the ground, and heat is just being conducted up through the atmosphere, but there's no moving air. It's just that the heat is moving, but the air is not. So that's called conduction. Right? You could have hot ground, colder air above, heat rising, but the air is still. Now, that can happen, but if the difference in temperature between the air way up high and the air down below is great enough, that is, if there's a big enough temperature gradient, then this conducting solution is unstable. And what happens instead is that the air does start to move, and the hot air rises, goes up, gets cooled off, and then sinks because it gets denser and comes back down, creating these circulating patterns called convection cells. And what does that have to do with this? The rotating water wheel is like a convection cell, whereas the steady water wheel is like conduction, where it's not moving. Okay. So, and here the driving caused by the water flowing in is analogous to the driving caused by the temperature gradient between hot and cold parts of the atmosphere. So that's the analog, and Malkus had all that in mind. He's an expert on convection when he designed his wheel. It was supposed to be a little model of a convection cell, kind of. So anyway, in that, if you think about it, what is this saying? It says that this state of steady rotation can exist if this is a ratio of something, numerator over denominator. What does it mean? The physical effects on the top tend to make the wheel rotate. That is, G and Q1 are driving terms. G, the strength of gravity, and Q1, the inflow. They tend to drive the wheel into rotation. In the sense that faster inflow or stronger gravity would tend to encourage rotation. Whereas these other terms are dissipative terms. This is drainage and friction in the brake. They tend to oppose the motion. K and nu tend to oppose the motion. By damping it out. And so you have this battle going on between the drivers and the dampers. And if the drivers win, then these rotating solutions exist. OK, so I think that's all I want to say then about the fixed points for the water wheel equations. Any last questions before we leave them? Yes?
The only point where the omega equals 0, a stable point is when
the question was, is the only time that omega equals 0 is stable when the tilt of the water wheel is 0, so it's just flat on the table? No. You can have a stable, non-rotating solution if the damping is strong enough, even with a tilt. So if the K and the nu are big enough compared to the, in fact, if this ratio is less than 1 rather than greater than 1, then these rotating solutions don't even exist. And the system just conducts, or in this context, doesn't rotate. We'll prove that later on, maybe even later in this lecture, that if this ratio is less than 1, for any initial condition, the system will end up getting stuck, not rotating. So it has a global attractor. And it'll be one of our first global results in the course. That is, we could prove it for all initial conditions, not just nearby to that state. But that's coming later. So for now, let me say goodbye to the beautiful water wheel and say hello to the even more beautiful Lorentz system. Actually, not even more beautiful, because they're practically the same thing. So, Lorentz equations. Now, don't be confused. There's a few other famous Lorentzes in science. This is Ed Lorenz we're talking about, who was an atmospheric scientist at MIT, died only a couple of years ago. There's also Lorenz with a T, TZ, that you learn about in physics with the Lorentz force. He was a contemporary of Poincaré. He's much earlier, and Einstein. He's 100 years ago. We're not talking about that Dutch Lorenz. And we're also not talking about Konrad Lorenz, who's the guy that taught the ducks to walk after him. You know, that is, the ducks were born and hadn't seen their mother. They thought Lorenz was their mother, and they followed him around. He was a behavioral biologist. Okay, that's neither of those. We're talking about Edward Lorenz, who is unfortunately no longer with us. I got to know him a little bit. Maybe I'll tell you some stories about him. He's a very charming and modest person who did a fantastic thing. I mean, the one story I guess I'll just tell at this point is I used to ask him to come talk to my class at MIT since I was there and he was there. And every year I'd say, would you come and give us a guest lecture? Because he's really one of the giants of the whole subject of nonlinear dynamics. And every year he would always say, well, what would you like me to talk about? And then I would say, how about the Lorentz equations? And he would say something like, oh, that little model, you know, because he wasn't, he felt like he had moved on and he wanted to tell you whatever it was he was working on now. So then he would always talk about something else, and it would be interesting, even though at that point, he was 80 years old, he was still working hard. And so, yeah, you couldn't get him to talk about his Lorentz equations. It's like if you asked Einstein to speak about relativity, and he said, that? Anyway, so Ed Lorentz, and I'm going to give you a handout. Actually, not a handout. I guess I'll put it on our webpage where you can read the original paper where these equations were presented, and also a chapter from James Glick's fantastic book about the history of chaos that tells the whole story behind them. But Lorentz's paper is actually very readable, and you should read it. It's fun. So it appeared in the Journal of the Atmospheric Sciences in 1963. Sorry, it's volume 20, 1963. And page 130 to 141. So as we've been saying, it's related to convection. He, in fact, derived his model from a simple model of convection. And why it's so significant, what he did, is that it's the first example of a system with a chaotic attractor. People had seen chaos before Lorentz. You wouldn't want to say Lorentz discovered chaos. That's not exactly true. Poincaré had discovered chaos in the late 1800s, but in Hamiltonian systems while studying the three-body problem in astronomy. But he didn't have a chaotic attractor. He had a kind of transient chaos. That is, the system would be complicated for a while, but it didn't. What's so different about Lorentz's example is that it was self-sustaining chaos. It would just keep going. And also, Lorentz's methods were very understandable, but yet way ahead of their time. And his paper was sort of obscure for about 10 or 15 years. And then in the 70s, when other people started to get interested in chaos for other reasons having to do with turbulence, they started to notice Lorentz's work. And then, I mean, it's interesting, if you look at a graph of the number of citations to Lorentz's paper as a function of time, you'll see it's like, 1 or 2 a year all through the 60s and into the 70s. And suddenly he gets discovered around 1975, and then boom, and then he's getting hundreds or thousands of citations a year. Anyway, so his equations look like this. X dot is sigma y minus x. Y dot is Rx minus y minus xz. And z dot is xy minus bz. So as you can see, it's another three-dimensional system, just like the waterwheel equations. And it's got parameters, which are sigma, r, and b. They're positive. The dynamical variables x, y, and z could be positive or negative. You may be wondering, what's the interpretation of them? Don't think about it too much. Just treat them as abstract quantities, x, y, z. It's not really relevant for us what this has to do with fluid dynamics. But if you really wanted to think about it, you could sort of see that they look very similar to the water wheel, in that, remember, the water wheel had two quadratic nonlinearities. It had omega A1 and omega B1. And those are somehow related to this xz and this xy, which are the only two quadratic nonlinearities in this. The jargon is that R is called the Rayleigh number, as we just discussed. But now it's recognized with its own letter. Sigma is named after another great fluid dynamicist, Prandtl. But I'm not going to really talk about that. It's just sigma to us. And then B doesn't get named after anybody. B is just something related to an aspect ratio in the geometry of the system. But again, we're not going to speak about the physical meaning of these parameters. They're just parameters. So as I say, there's only two nonlinearities, quadratic, both of them. The xy and the xz terms. And another homework assignment or homework example I want you to look at, I think I assigned it, maybe I didn't, but if not, you should look at it on the next assignment or maybe the previous one, is that the waterwheel equations actually can be mapped into the Lorentz equations. That is to say, they're a special case of the Lorentz equations, a little less general, under a change of variables. And I give you some hints about what the change of variables needs to be. So they're just slightly less general, the waterwheel, but very similar. I think you'll find that one of the parameters might be like sigma equals 1 or something in the waterwheel. I can't remember. But anyway, it's only a little bit less general. The other thing is that the Lorentz equations are not restricted to these fluid systems with water wheels or convection. They also come up in other parts of science. So they, what I guess was a surprise at the time, they also arise in models of lasers. That was discovered by a laser physicist, Hermann Haken. And they also arise in studying dynamos in connection with, I think, maybe like geosciences, the magnetic dynamos powering motion in the core of the Earth, of the, I don't know, not really sure. Anyway, so they do come up in other parts of science. Now, let's start talking about some of their properties. That is, want to observe some things about this system that are just very elementary before we get into the hard stuff. Just to clarify, our philosophy here is going to be that we got this daunting three-dimensional system. We don't have any real technique besides fixed points and linear stability. So we'll do that. Then we're going to try to throw everything we know at this system in a way mimicking what Lorenz did, because no one had really studied much about three-dimensional nonlinear dynamical systems. So we'll look for limit cycles, we'll look for bifurcations, and we're going to find that in a certain regime of parameters, everything that we know is impossible. That is, it doesn't have stable fixed points, it doesn't have stable limit cycles, doesn't have quasi-periodicity. So, but it does something. What does it do? And that was actually the kind of reasoning that Lorenz used to, in the style of Sherlock Holmes, that after you've ruled out the impossible, as he says to Watson, whatever remains, however improbable, must be the truth. So in this case, whatever remains will be something unprecedented, which is going to be chaos. So let's follow that reasoning by first going, trying to understand the simple parts. Well, Okay, one thing you might notice is that they have a symmetry in them. That is, they are symmetric under the change of variables where we take xy to minus x minus y, keeping z the same. What I'm saying there is if you look at the equations and replace x by minus x and y by minus y, the equations don't change. Do a little fluid dynamics here with this bucket. That is, suppose you change the sign of x and y. Then in this parentheses, y minus x will change sign, but x dot will also change sign. So those negatives will cancel out. Down here, if you change the sign of x and y dot will change sign, so will rx, so will y, and so will xz because we haven't changed z. And down here, nothing changes sign because the negatives in x and y cancel. So what does that prove if the equations are symmetric with respect to this? It means that if we have a solution of the equations x of t, y of t, z of t, if this is a solution, then it has a symmetric partner solution. That is negative x of t, negative y of t, z of t is also a solution. Of course, it might have a different initial condition, but you can think of it as solutions come in pairs if they're distinct. If they're not distinct, I mean, if they're actually the same, then it means that the solution itself possesses this symmetry. And so we'll see things like that, where you either have symmetric solutions or a symmetric pair of them. Another thing, I think we mentioned that pitchfork bifurcations are common in systems with symmetries. And so this already leads us to suspect that when solutions bifurcate, they might tend to do it in a pitchforky way. And we already saw that when we saw that omega squared enters the fixed point equation for the water wheel. That is, if there was a plus omega rotation, there was also a minus omega. That's just an example of this symmetry rearing its head. Now, here's a new property for us. We haven't talked about this, but then this is going to take a little time. This system has a very convenient property that it is dissipative in a technical sense. That is, in the sense that volumes in phase space contract under the flow. And so let me explain what I have in mind there. You want to think about, okay, I mean, if you have one initial condition, you know how to think about that. You have an initial condition. It's now living in a three-dimensional space. And as time goes on, a trajectory flows from that initial condition and makes a curve in this three-dimensional space. Then imagine instead of one initial condition, imagine a whole potato shape filled with initial conditions. That's a solid volume of initial conditions. Then each of those points in the potato, like if I draw a little picture, so here's my potato, and it has, as I say, some initial condition here, and then as time goes on, maybe it flows to there, but then this initial condition does something else and flows to here, and if we do this for all the points in the potato, the effect will be that we're going to get a deformed potato over here, you know, which is then the image of this potato under the flow. It doesn't have to be a potato. It could be a sphere, any shape you want. I just want you to think of it as fairly generic three-dimensional blobby shape. And so the claim is that for the Lorentz system, whatever the volume is of the initial blob, it will steadily shrink as time goes on. That's what I mean by dissipate. If it's getting squashed in terms of volume. That doesn't mean it's shrinking uniformly in all directions. It might be getting squashed in some directions and spreading out in others, but its total volume is shrinking. Yes? I'm going to get the conclusion right now. The question was, how do we get that? Right. So we have to figure out how do you calculate how volume changes over time in phase space. Yes? The question was, does this mean that all trajectories have to approach the same point as time goes to infinity? Not necessarily. They just have to approach a set with zero volume. But things can have zero volume but still have area. Like they could be a flat pancake or something. Anyway, this is what we're going to think about. What is that limiting set? It's going to turn out not to be a pancake. It'll be more complicated than a pancake. But I don't want to give away too much yet. It's fun to be bewildered for a while. So they can also evolve, by the way, to a point, like you said. Or they could all evolve to a limit cycle, which has no volume either. Right? I mean, that's conceivable. So anyway, let's see how do volumes evolve. Well, so let's just imagine picking a generic volume in phase space. Let's think of this as our volume V of t. And then points on its surface are what we need to keep track of. Because you could sort of imagine that it's the points on the surface that will map into points on the surface here. This shape is not going to turn itself inside out, though I'm not going to prove that, but hopefully you could sort of believe that. So points on the surface are what we should keep track of, and they flow according to the vector field. And let me do it fairly generally for any vector field, not just for the Lorentz system. And so let's ask, if we just look an instant later, what is the volume of the blob at time t plus delta t? So that's how we're going to derive a differential equation for the volume to see how does the volume change. And by volume here, I mean actually the number, not the region. The amount of volume in the changing potato. So I want to give you an intuitive argument here, as usual. That is, let us think of a vector x, that's shorthand for x, y, z. And let me use the notation u is x dot. And so that's velocity in this three-dimensional phase space. Meaning, our usual thing. We think of a vector field in phase space when we have a differential equation. That tells us the vector at each point. Now, I want to distinguish. Don't be confused that we've been talking about fluid dynamics where there is an actual velocity in a real physical space with fluid moving. We're not talking about that. We're just talking about this abstract velocity in phase space. though it's often convenient to pretend that there's a fluid moving around in phase space, and so maybe I'll think that way, but it's not really physical. Okay, anyway, so I've got U. Now, let's think in terms of what is the outward flow, or the outward component of that velocity on the surface. It's going to be U dot n, or x dot n. This is an important quantity. This is the normal outward velocity on the boundary that is on the surface that's bounding the potato, on the skin of the potato, which in math we often write as, it looks like partial derivative, but I don't mean partial derivative. I just mean the boundary of the volume. Think of it as S if you want. So, you know, here's the blob. It's solid. And here's the surface boundary of V. The stuff inside is V. And now we want to ask, what is the volume at time t plus delta t? And so think of it, let's, for visualization's sake, think of the potato as expanding. But nothing I'm going to show will depend on that. But if it were expanding, then you'd have, you know, at some later time, some bigger potato out here. And that might be because this piece of the surface has expanded over to here. Now, we have to keep track. The normal vector, remember, is at right angles to the surface. So here's n. And I'm using the standard convention that n is unit length. So it's the outward unit normal. And the vector field is not necessarily parallel to n. Like at this point, remember, we're in phase space, so there's a vector at every point. At this point, the outward, at this point, the velocity vector field might be, say, like this. So that's not supposed to be tangential or normal. That's just supposed to be a generic vector. So this is what my U looks like at that point. You know, and at this point, maybe it's like that or something. This, I guess, was supposed to be my n here. No, well, I think that was actually, sorry, I'm not going to say anything about that. That was supposed to be where that patch of surface moved. But here's the thing I want to do now. Instead of looking at this picture, I want to sort of simplify the picture. Here's the intuition, that the way that this expands is due to the normal component of velocity on the surface. The tangential component of velocity just sort of slides the surface along itself and doesn't cause any volume expansion or contraction. It's the outward motion of the surface that causes expansion. And so that's why I'm singling out U dot n, because the normal outward velocity is what's going to matter. So the claim is that V, an instant later than t, is going to be the original volume plus the volume swept out by tiny patches of the surface integrated over all patches. And so the intuition here is that we're just trying to think of each little patch on this surface. There's a little patch. And that little patch is flowing as time goes on. That is, all its initial conditions in there are moving according to the vector field, sweeping out a new volume, which sort of in side view might look something like this. This is an infinitesimal patch blown up big, so you can look at it. It has area that we'll call dA. And what I was trying to convey is that this thickness that has been swept out, that is this distance here, is going to be U dot n. That's the outward normal velocity, dot being dot product, of course. U dot n, that's the outward velocity, and then times this amount of time, delta t, that we're imagining integrating over, or allowing the flow to occur. So u dot n times delta t would be this distance. That's how much the surface has moved in that direction. And to the extent that we've picked a tiny patch, this thing will be sort of like a little rectangular box. That's the intuition. And so what I'm trying to do is, in this intuitive way, claim that the change in volume due to this little patch of area will be delta V from this piece is going to be approximately U dot n delta T, which was this thickness, times, maybe it'll be a parallelogram, but it will, a parallel pipette or whatever it's called. But it'll have this dA times this thickness, and that'll be the change in volume contributed from that one patch. And so then I said what we're going to do is add up all these patches. And so the heuristic argument that I'm trying to give is to say that V at time t plus delta t will be approximately V at the original time t plus integrate all these little contributions. So that will, the delta t comes outside the integral, and I get U dot n dA. I've integrated now over the whole surface boundary of V. If you're used to thinking in multivariable calculus, this is actually a double integral. Right, it's a surface integral. If you like thinking in terms of flux, we're talking about the outward flux of the vector field U. And yes?
Why is it not exact?
Oh, okay. The question was, why is it not exact? It will be exact if we take the limit as delta t goes to 0. Yes, that's right. So going just a step farther, then let's subtract this v from the left-hand side, divide by delta t. And so as you already anticipated, what we're looking at is the limit of v at t plus delta t minus v at t all over delta t as delta t goes to 0. Well, on the one hand, that's just what we mean by v dot of t. But on the other hand, based on this formula, we're getting, I divide by delta t, that this should equal the double integral of u dot n dA, integrated over the surface boundary of V. So yes, this would be exact. And then the last thing to notice is, this is one of the formulas that I wanted to derive, that this tells me how volumes evolve. The rate of change of volume depends on this double integral. And then the last thing is, this double integral might look familiar to you if you have recently thought about multivariable calculus. That is, integrating u dot n dA over a surface. Do you see where I'm going? This is all set up for the divergence theorem. Right, so this is equal to the triple integral of the divergence of u, which we could write as del dot u d volume over the volume. So from the divergence theorem, we get that. And so this is the interesting sort of set of little equations that tell us how volume evolves in phase space for any vector field in 3 dimensions. I think it will work in any dimension, actually, but let's stick to 3. So far, so good? OK, so let's specialize that to the Lorentz system. Okay, so where are we? We've got V dot is this triple integral divergence of u dv over the volume. And now, what is the divergence of u for the Lorenz equations? Well, so the Lorenz equations, let's recall, had x dot is sigma y minus x, y dot is rx minus y minus xz, and z dot is xy minus bz. And so u was the vector x dot, y dot, z dot. Right, because it's the velocity in phase space. And so when we take the divergence of u, then that will be partial x dot partial x plus partial y dot partial y plus partial z dot partial z. And now we just apply that to the Lorenz system. So partial x dot partial x gives us a negative sigma. Partial y dot partial y, there's only this term here, gives us a minus 1. And partial z dot partial z gives us a negative b. And notice it's all negative. That is, we're getting negative of sigma plus b plus 1. So it's strictly less than 0, since sigma and b are positive. And so, and actually it's beautiful, it's constant. That's really nice. I mean, aside from being negative, it's constant. So our equation becomes extremely simple. It says v dot is this constant. I mean, think about it this way. If I ask you, do a triple integral of a constant d volume, the constant comes outside, and then you're integrating d volume. You get the volume. So we get v dot is minus sigma plus b plus 1 times the volume. So you learn from this that for the Lorenz system, volumes shrink exponentially fast. So v of t is v of 0, e to the minus sigma plus b plus 1 times t. And of course, Lorenz understood all this. This is an argument straight from his paper. So we've got this situation where you start with a blob of initial conditions, and as time goes on, sort of like a balloon having the air sucked out of it, it's going to shrink down to 0 volume, no matter what. And that's pretty powerful. Powerful thing to keep in mind. So volumes shrink exponentially fast in the Lorenz system. Is there any question about this argument? So the implication is that all the trajectories that is, think of picking a volume which is, you know, like all values of x, y, and z less than 1 billion. That is some giant cube, which is all reasonable initial conditions. Then, because exponential collapse is so fast, that giant cube, which encompasses every initial condition you could think about, will eventually, that cube will shrink down to a set of 0 volume. And so that means that all trajectories end up on some limiting set of 0 volume. Zero three-dimensional volume. And so what could such a set be? Well, I mean, it could be various things. it depends on the parameters then. So the set could be a point. It could be a cycle. You might imagine it could be a surface of some kind, but that is not seen here. It doesn't, like, for instance, get attracted to the surface of a torus. That will be impossible for reasons we'll argue later. So you can't have quasi-periodicity. So if it's not a point or a cycle, because we're going to see later that under certain conditions those can be ruled out, then it could be an object of a type we haven't seen before, which we're going to call a strange attractor. That was not a term that Lorenz used. That term came later. But yes, so Lorenz absolutely did understand about the existence of a strange attractor in his system, and he talked about it, not in those words, but he tried to understand it as what he called, I really love this expression, he called it an infinite complex of surfaces. And today we would call it a fractal. But he absolutely knew that he had a kind of fractal set of surfaces in his system as an attractor. And he even tried to draw pictures of it with primitive, I mean, he didn't have computer graphics, but he had some artist sketch what he thought he was seeing in the computer. So we'll get to that. But anyway, and we'll also try to understand why does he say it's an infinite complex rather than just one surface. But I still have a little bit of time here, so I think I want to show conditions under which this limiting set can be a point, because that's another classical calculation that's not hard. Actually, maybe I'll save that for next time and just quickly talk about some linear stability, which is probably the first thing we should do. Well, all right, conveniently, we've still got the Lorentz equations up on the board there. And so, although we talked about the water wheel, we didn't actually start analyzing the fixed points for the Lorentz system. So let's just quickly crank them out. Rather than belaboring the algebra with all the numbering equations, I'll just trust you can find them. So you can show that they are, well, one of them is x, y, z equals 0, 0, 0. The origin is a fixed point. And that's true for all values of the parameters. We're going to think of sigma and b as not really parameters. The traditional view of this is that you're going to change r, the Rayleigh number. That's the control parameter you have easy access to. So from now on, think of sigma as just frozen. Actually, Lorenz chose their values. Sigma equals 10, and b equals 8/3, if I'm remembering right. I'll have to check that later. Those are the traditional values for the Lorenz system, for reasons that Lorenz explains in his paper. But we think of r as a control variable, parameter that we can change. Anyway, so this origin is always a fixed point. Now, it's not always stable. This is sort of like no rotation of the water wheel. Then there's, so I'll just say over here, often assume this. So for now, we can think of it as general sigma and b. Anyway, there's that. And then we also have fixed points which are of the form x equals y, and both of them are equal to either plus or minus b times r minus 1, all inside a square root. And z, it would be r minus 1. So that's another fixed point that you can check exists. But there, as you can see from the r minus 1 inside the square root, this exists only if the Rayleigh number is big enough, if r is bigger than 1, sort of like what we had previously, where the Rayleigh number had to be big enough for the water wheel to be stably, or not stably, steadily rotating. Okay, so there's that kind of fixed point. And Lorentz, notice these are symmetric. There's a symmetrical pair of them, the plus pair and the minus pair. And Lorentz calls them C plus and C minus. Where I guess C for convection, because he thinks of these as the steadily rotating convection patterns. And also notice that as r approaches 1 from above, these convecting solutions, well, as r goes to 1, x, y, and z all go to 0. So these, you can see, are now born out of the origin in some kind of bifurcation. And that makes sense because we already are guessing that this system will have pitchfork bifurcations, and this is an example of, it'll turn out this is a pitchfork. There's a pitchfork bifurcation at r equals 1. That turns out to be a supercritical pitchfork. That is, when these fixed points are born, they're stable. First, let's comment on the local stability of the origin. So, well, what should we do? So for the origin, we're speaking about x, y, and z being small. And so to read off the linearization here, we could write down Jacobian. We could also just look at it, because we're just asking if x, y, and z are small, ignore the quadratic terms. And so the linearization can just be seen from inspection. You get x dot is sigma y minus x, y dot. That is, by just ignoring the quadratic nonlinearities, we get y dot is rx minus y. And z dot will be minus bz. And so you can see the z equation has decoupled from the rest, and it just has exponential decay in the z direction. So z of t goes to 0 exponentially fast. In the linearization, don't think I'm saying this about the system in general. This is for the linearization in the neighborhood of the origin. So the z's decay. And then we have this little two-dimensional system for x and y, which we can think about separately. So x dot is, well, let's do it in matrix form. X dot, y dot, then is the matrix minus sigma, sigma r minus 1 times xy. And using our 2D techniques, we can think about what does that imply for the xy dynamics. And, well, let's look at the trace. That's minus sigma minus 1, which is less than 0. The determinant is sigma times 1 minus r. And so when r is greater than 1, we have a saddle point at the origin. Because we have a negative determinant in this 2D space. So here's a slightly interesting thing if you haven't thought about this before. it's a new kind of saddle point. We're in 3D. So in 2 dimensions in the xy plane, we have one direction coming in and one going out. But then we also have the z direction coming in. We have collapse. So it's a saddle point with 2 directions coming in and one direction going out in 3D. Right, so as a 2-dimensional stable manifold locally and a 1-dimensional unstable manifold, meaning a curve, unstable curve coming out of there. And then we should also think about, is it a node or a spiral as far as the 2D system is concerned. So we look at tau squared minus 4 delta, which here would be sigma plus 1 squared minus 4 sigma 1 minus r, which can be written as sigma minus 1 squared plus 4 sigma r with a little bit of algebra. And that expression is positive. So in fact, tau squared minus 4 delta is always positive, which means that we do not have, in this case where suppose r is less than 1, so we don't just have a saddle. So if r is less than 1, then the delta is positive, but tau squared minus 4 delta is also positive. That would mean that we have, and since tau is negative, we have a stable node. Yeah. If r is less than 1, origin is a stable node. Where now it really means in all 3 directions, x, y, and z. Any question about this linear stability thinking? So then what we want to do next, and this I don't want to start now because it's too much of a calculation, is to say that something much stronger happens, that when r is less than 1, in fact, the origin is globally stable. That is, not just to neighboring trajectories, but all trajectories will end up at the origin. So we're going to need a new technique to prove that, called Lyapunov functions, and we will develop them next time. Okay, thanks.